All right, we're talking about concavity today. This is the next big thing, which has a lot to do with the second derivative, actually, and we'll talk about that a little bit. So far, we've done everything that's been involved with the first derivative, okay? So we found, basically what we've done so far is we found the first derivative where it equals 0. That sets up our test intervals. We can find out where it's increasing and decreasing. We can use the first derivative test, which says if it switches from increasing to decreasing, it's a relative max, assuming that's a critical number. And then likewise the other way, it makes it a minimum if it's decreasing to increasing. Okay, that's the stuff we've done so far. Okay. Now, as far as this graph is concerned that we're taking a look at, we want to talk about concavity, which I don't think we've talked. We might have talked about this a little bit pre-calculus, but probably not. I think we talked about increasing and decreasing mostly. But what concavity is actually it's a more specific type of increasing or decreasing. Okay? If I'm talking about an increasing section, and we'll get to this graph in a second. If I'm talking about an increasing area of a graph, I can actually have two different kinds of increasing parts. I can have an increasing that looks like this, or I can have an increasing that looks like this. Either way, the slope of those are going uphill. Okay, either way, this guy or this guy, as I go left to right, reading the book, right, it's going to go uphill. So the slope of this is going uphill. Okay, both of those are said to be increasing. Okay, if I did decreasing could be two different ones. It could be this decreasing, or it could be this decreasing. It could be either one of those. Okay. Once again, still, the stuff that we've done before. That all applies to the first derivative. Okay, first derivative tells us slope. That tells us if it's going up or going down. That's what we're looking for. Okay? Concavity is a little bit more specific type of increasing or decreasing. If I were to look at these two different, you can see the difference between those, right? This one's got kind of an underneath slope right here, and this one's got kind of an over the top one right here. This one they call concave up. Concave up. And this one they call concave down. Okay, and it all depends on, I always think of these as far as like a cup. If I were thinking about this as a cup, which way is it pointing? This one right here, if I were to finish this cup out, this cup would be pointing up, so they call that concave up. It's going up, okay? This guy is pointing down, so it's concave down. The book has a little bit more formal definition of it, but their formal definition is if I have a shape that goes like this, which is a little confusing because right here this is both increasing and decreasing, right? You guys would agree with that? At this point right here it switches from increasing to decreasing, right? That would be a critical number. But this one is concave down all the way, okay? On this whole entire interval. So it's a little bit different on the both once we switch those. Now, what they say for concave down is they say if I pick a point right here and I draw a tangent line at that point, right? Notice where the tangent line is. The tangent line is above the graph. Okay? If I pick this point right here and draw a tangent line, the tangent line is above the graph. The entire tangent line is above the graph. Anywhere I pick on that little region right there, the tangent line is above the graph. So they call that a concave down because the graph is below all of the tangent lines. Okay? So that's the kind of the book definition of it. And then like vice versa, if I had a concave up, which would be an upwards cup, all the tangent lines are now below it. All the tangent lines are on the bottom if I were to do all these tangents, right? And so the graph is above all the tangent lines, making it concave up. So it depends on which way you want to think about it. I always think about it as far as like a cup type analogy for me. But if I were to go back to my initial graph right here, and I just want to identify where the intervals are for where this guy is either concave up or concave down, that's what I'm searching for. So right here, if I look at this little part right here, it would be concave down on this entire region right here. Okay? Ignore that this point right here is the maximum and that it goes from increasing to decreasing. We're not too worried about that right now. We're worried about this guy being down the whole entire way. So this section from here all the way here is going to be concave down. Okay? We'll just say CD. And then once we get to this point it kind of looks like a value that might be important, right? It's a sharp turn, right? We can't differentiate there, but it's a sharp turn. And it could switch. Well, it looks like once I hit this point, it looks like it's concave down again, right? And it goes right to about here, right to about this point right here. It's still concave down. So it's actually concave down all the way through this point. Now this point is where it switches. Okay, it switches from going down right here, and then it switches. Now this is concave up. Okay, so now I've got a concave up from this left point right here, this point right here, that's where it switches, all the way to this point. Okay, so I got concave up to here. And then, looks like I go here, this is concave up, and then right in about here somewhere, looks like it switches again, right? So right here, I'm going to say this is concave up still, switches at this point, starts going concave down, right? And right about in here is where it switches again, concave down, switch here, and this is concave up for the rest of it. Okay, so there's a whole bunch of different intervals where this guy can switch. Does that make sense? Kind of? Okay, cup down, cup up, that's kind of the thing that I always think about. Okay, now the points where it switches are the key points that we want to look at today. That's these three right here. Okay, these are all called inflection points. And that's kind of the new terminology for today, inflection points. Different than critical numbers. Okay, critical numbers are where the derivative equals 0. Inflection points are where the concavity switches. So it's where it goes from concave up to concave down. Okay, now this one right here, they wouldn't call an inflection point because it's not switching from one to the other as far as concavity is concerned. I'm going concavity down to concavity down. So this point right here is not an inflection point. Okay, this point it switches, right? So it's an inflection point, goes from one to the other. Doesn't switch here, so not an inflection point. Here this one switches, inflection point. Here this one switches, inflection point. Okay? Feeling pretty good about that? Okay, so that's the main definition of an inflection point is concavity switching is what we're talking about. I looked it up in my other book and I couldn't find it.
It's the x coordinate.
That's I know, but why'd they label it as a? Yeah, that's what I was thinking too. It was driving me nuts.
I googled.
Oh, what would Gumke? What would Gumke do, right?
What would Gumke do? So I googled.
Nicely done.
Okay. It's the x coordinate.
I went and was ranting with him this morning about it. All right, I think our book does something wrong on this part. So, anyway.
Wait. How could the book be wrong?
Yeah.
The math
The math gods are wrong. The math gods were wrong in this group. They tried to be so specific, and I think they missed the boat. I could be wrong too. You know, I'm still a newbie at this stuff. So, in comparison to the math gods, so they've been around forever.
Oh my gosh.
You're the super noobs. Really. Okay, so we feel pretty good about this. It's not too bad, I hope. Now I know a lot of this is theory. And we haven't done any actual problems yet. I still want to stay on the theory track just for a little bit to kind of develop how we're actually going to do this. Okay. So the first graph we're going to look at is going to look like this: y equals 1/3, x to the third, and then minus x. The first thing I wanted to just graph this and just take a look at what the graph looks like. And I know we haven't done too much as far as like graphical interpretation between a graph and then the graph of its derivative, which we'll get into a little bit later. But if I were to just graph this guy, and I'm going to try to be, fairly precise in my graph. It's not going to be perfect, but it'll be pretty close. Go here, and go here, here, here. Okay, so let's say that's our graph. Yay. Now, just as far as looking at the graph goes, hopefully we can look at the graph and try to identify concavity, to determine if it's concave up or concave down. We could probably determine derivatives, right? We could probably determine relative max and relative mins just by interpreting the graph. Just by looking at that graph, you can tell a lot about the graph, right? Obviously, it looks like a relative maximum would happen at -1 and then however high it is. Relative min, maybe a +1. And then I would say no absolute max or no absolute min because it looks like this might go forever. Okay? Now, what about concavity? Where would you guys think this is concave up or concave down? Where is it concave down?
Judging that these are 1 increments, right?
Yeah.
Then from 2 to 0 would be
-2 to 0. -2 to 0, or negative infinity, depending on what the graph was, right? Either one of those. To 0, you would say that's concave down, okay? And then right here at this point, right, it switches, right? It goes from concave down to up, right? So this point right here, they call this the inflection point. Okay, now that inflection point, we want to mess with that just a little bit, okay? We also want to mess with the derivative and what the graph of this derivative looks like. If I were to graph this guy, first off, if I were to take the derivative of this guy, that would be pretty easy to do, right? What would the derivative of this guy be? X squared minus 1, right? Which is a pretty easy graph to graph. Okay, let's say I were to graph that guy. That just means go down 1 on a parabola. And it means go like this, and it should be at 1 and 1 like that. Okay, so that would be my derivative function. Okay, now what we've done so far, and we've hit on this very lightly, okay, but we've looked at this graph right here, and let's say I was looking at this relative maximum point right here. Okay, what's the slope of this point right here? 0, right? Now the slope is interpreted as the derivative, which is this function right here, okay? Notice where the derivative equals 0. Where does this function run into the axis? Right here at -1 and right here at 1, okay? See that connection? Maybe? Okay, so the slope right here is at 0. Slope right here is at 0. Okay, so those slopes are both at 0. So if I looked at the derivative of the graph, those are both the points where that graph, the derivative, actually equals 0. So where the derivative equals 0, we'd set that equal to 0 and solve for it to find critical numbers, right? That would give me these two values right here. Okay, so that's my first step. I think everybody's okay with that. Now let's say I took the derivative of this guy. Let's say I did the second derivative now. Write this down here a little bit. Second derivative, what would the second derivative be? 2x, okay, so 2x is my second derivative. If I were to graph that, that's just a line with a slope of 2, so my graph is going to look something like this. Okay, so that's the graph of the second derivative. And once again, I'm trying to connect the points here if I can, okay? Now, what I'm looking for is from my first derivative, if I wanted to find these points right here, I looked at the first derivative and find out where it crossed 0. That gave me my relative max and relative min. Gave me my critical numbers, right? Well, what about this inflection point? If I look at the inflection point, which is right at 0, and I go to the derivative of the graph, right? What happens right at 0? It's a critical number of the derivative. Ooh, critical number of the derivative. That's why they call that the inflection point, okay? Well, look at the derivative of the derivative. The second derivative, where does this guy cross 0? Right at 0, okay? Well, that makes sense, okay? So that's how the graphs kind of flow together with the second derivative. So, if you want to find inflection points, all you have to do is find the second derivative and set that guy equal to 0. Okay? That'll give you what they call the inflection points, okay? So we solved that. It also works not only where it equals 0 or where it's undefined. Okay, so just like critical numbers, you set it equals 0, and where it's undefined, that gives you possible critical numbers. Likewise, for the second derivative, set it equal to 0, or set it equal to an undefined. So make the bottom 0 or something like that, and then that'll work for you. That'll get you your second derivative. Okay? Yeah.
So if you have a fraction thing and if it's undefined, it's also...
It's still an inflection point, right? Now, that's what we were kind of arguing over, because if it's undefined and the graph is undefined at that point, it's hard to have an inflection point that's not there, because it's a vertical line, you know? So that's why I think our book is wrong, because they actually say it's a point, but it can't be, because there's not a point on that graph that works. I know, it's driving me nuts. So we have to think of it not as even though I call it an inflection point, I'm actually concerned about the x value. So I'm talking about like the x value -1 or the x value 0. I'm not actually thinking of this as some ordered pair, some point. Okay. So although they write it as an ordered, and I think it's not correct, because on some it's like literally not there. It's on an undefined asymptote. Anyways, let's do a couple problems, okay? All right, so the second derivative is pretty powerful, okay? Now, one thing we want to find here is we want to find out where the second derivative equals 0. That gives me my inflection points. That also tells me on the intervals for which this guy is going to be concave up and concave down. For it to switch from concave up to concave down, it has to switch at an inflection point, okay? So if I find out where those possible inflection points are, that's how I set up my test intervals to find out if it's positive or negative. So if I were to do this graph right here, this 1/3 x to the third minus x, and I want to set up my intervals for where this is concave up or concave down, I would set up my intervals based on that, based on this guy right here equaling 0. X would equal 0. That's my inflection point, okay, or possible inflection point. Now I set up intervals. I go from -infinity to 0, and then I go from 0 to infinity. So those are my test intervals that I want to test. Now what I do is I pick a number in that interval, and no matter what, I'm going to plug that into the second derivative to find out if it's concave up or concave down. So I'm going to pick the second derivative of some number inside that interval. Okay, so I'm going to pick, like, let's say -1. Okay, if I plug -1 into the second derivative, that tells me if it's concave up or concave down. It tells me how it's increasing or decreasing, depending on which it is. Okay, I would do the same thing here on my second derivative. Plug in a positive value of 1. And find out if it's concave up or concave down. So I'm just going to plug in the value of -1 into my derivative, my second derivative function, which is -2. Remember, I don't care about the value; I care about the sign. That's negative. Okay. So this guy is going to be a negative value right here. Okay. If I plug in a 1, this gives me a positive value. And so if I think about the graph, that means anywhere from -infinity to infinity, this guy's got to be concave down. I get a negative value for my second derivative; it's got to be concave down. Okay, I get a positive value for my second derivative on any point in there, and that's going to give me, that's a funny looking C, concave up. Okay, so that's how I'd be checking that. So very similar to how is this increasing or decreasing, right? You find out the intervals on increasing and decreasing just with first derivative. This is the exact same with the second derivative and concavity. Okay, it tells you if it's concave up or concave down.
This is kind of what we first started talking about, but you know how it's concave? Yeah, kind of like if it's concave, how do you know it's an inflection point again?
If it switches from one to the other. So see how it goes from concave down to concave up? That right there is where it switches.
How do you know where exactly? Like, because it's in the middle of them. Is that?
It's gonna be hard to eyeball, right?
Okay.
Now, relative max, relative min, we can kind of eyeball those and
Yeah.
guess a little bit, right?
Yeah.
But it's really tough to eyeball concavity, or
Okay.
I'm sorry, it's tough to eyeball points of inflection.
Okay.
Yeah.
Okay.
Now, another thing to catch on to here is just because it's equal to 0 or it's undefined doesn't make it an actual inflection point. Because if I were to do this funny looking graph right here, right, and if I were to get this point right here, this point, what's the slope of this point right here? Undefined, right? You can't take the derivative of that at a sharp turn, okay? That's an undefined slope. If I were to take the second derivative of that still might give me a potential inflection point, right? But that's obviously not an inflection point because it didn't switch from concave down to concave down. Okay, or it didn't switch from one to the other. It stayed the same. So that's not an inflection point. Inflection point has to be where it changes. Okay, so even though it might have been undefined, which would be on this case, it doesn't make it an inflection point. It just makes it like potential inflection points. Kind of like critical numbers. You know what about critical numbers? We got a whole big list. It doesn't mean all of them are relative max, relative min, right? Only some of them were. Okay. However, it has to switch at an inflection point, or it has to relative max, relative min at a critical number. So. All right, let's do a couple of these problems just to kind of get the flavor of the idea. But I think we got like the theory out of the way. I think maybe I bored you enough with that. So let's do some real problems now. Huh? Now, eventually, where we're headed is to graph some of these graphs with literally no graphing calculator, which is kind of cool. Now, as we're learning, it's okay to use them and use them as an aid to help you at least see. So just to kind of confirm your answers, make sure that you're doing things correctly. But our goal is to try to ballpark this stuff without doing too much on the graphing calculator. Remember, half the test is no calculator, unfortunately. So as far as this is concerned, I want to just discuss the concavity here. That's the weird directions that they'll give you today. Is just talk about concavity. Is it going to be concave up, concave down? And where? Okay. So the first thing I would do is I would find out the second derivative of that guy. So the first derivative would be pretty easy here. Well, both are going to be pretty easy, I think. This is going to give me a 4x to the third minus 12x squared. And I want to find the second derivative. The second derivative is going to help me out with my test intervals. It's going to give me my possible inflection points. Okay. So second derivative of this guy. It's going to be, what, a 12x squared and then minus 24x. Something like that. Okay, so I'm going to set that equal to 0 or set it equal to an undefined value to find out whether the denominator equals 0. This one, however, is, as they would say, continuous and differentiable across the entire real number line. Oh, yes. I'm trying to say that a lot. So I want to solve for that, so I just do a quick little factor there. So I take out a 12x, and then I'm left with x minus 2 equals 0. And so I get 0 and 2. So 0 and 2 are my possible inflection points. That's where this guy could change from either a positive or positive to a negative or whatnot. Okay, so I'm going to set up my test intervals. My test intervals for this one would be negative infinity to 0. It'd be 0 to 2. And then 2 to infinity. Once again, you have a little bit of free reign on values that you're picking in here. You get to pick whichever ones that you want, and you want to plug these ones into the second derivative to find out where it's concave up or concave down. So for my second derivative, let's see. Second derivative, pick a number in there like negative 1. Second derivative, pick a number like 1, and then second derivative, pick a number like 3. And you can pick whichever numbers that you want. It doesn't really matter. But you just want to plug those numbers into your second derivative right here and find out just the sign of it. That's all you're caring about is the sign of those values. Okay. Well, this would be a negative 12, and this would be a negative 3, so that would be a positive number, whatever that number might be. If I plug in a positive 1, that would be a positive 12, and then 1, that would be negative, so this would be a negative number. And then if I plug in a 3, it's going to give me a positive and a positive, so this would be a positive number right here.
Can't you also plug it back into the original table?
Plugging it back into the original function will give you the values of them. It'll tell you how high it is, but it won't tell you if it's concave up, concave down, anything like that.
Because that's what I just did, and I got the same.
You got lucky.
Also, it has to be in the second derivative.
You got to do it in the second derivative for concave. Yeah, you want to plug it in the second derivative. Yep. So that tells me a whole heck of a lot. It tells me that I went from a positive number right here, which means I'm going to be concave up. So that means that the graph from negative infinity is going to be concave up. Okay. From 0 to 2 is going to be concave down, so concave down. And then positive right here, so back to concave up. Okay, so those are my intervals for which this guy is concave up or concave down. Okay, so I do have so both of these guys are inflection points, right? Because it switches, right? It goes from concave up, concave down to concave up. Okay. All right, now what about like relative maximum, relative minimum? I know we can get a lot of this stuff confused, but if I want to find critical numbers now, these were my inflection points. If I want to find critical numbers, I would set this guy equal to 0 and try to solve for those points. Okay, that would give me my possible relative maximum and relative minimums. Okay, so that's the stuff I'm looking for. What's up?
Just got this.
What is it?
My mom was sending me to the doctor.
Oh, have fun. Yeah, you're fine. You'll get a lollipop after you're done. But I need everybody to start calling him Georgia. Okay?
Okay.
Trust me. Georgia or Bruiser, one of the two. Whatever mood you're in.
Why Georgia?
Georgia
better.
Yeah,
Likes
Peaches are alright. Yeah, peaches are alright. So we can find out relative max, relative min just by finding those critical numbers right there. So we've got critical numbers. What was I going to say? Oh, we can solve for that for critical numbers. You guys are all good with that, though? You feeling pretty good about that? Now, we have to do what's called the second derivative test. We'll do that in a little bit. I want to do one more just to make sure our brains are okay on this stuff, and then we'll feel pretty good. Now, did anybody graph that and just kind of confirm our answers there? Just to make sure our concavity was good? I feel pretty good about our answers, so I'm happy. Yeah, what's up?
I'm kind of confused. Okay, so on the concave up, since it's positive on like the part, the negative infinity to 0.
Okay.
How do you know that actually makes a thing? Because it couldn't just be going like.
Could be going one or the other, right? It could be going one or the other. You're talking like because it's concave up. Concave up could be one of these guys, right? Or it could be one of these guys. Both those are concave up, right? Is that what you're asking? Like which one of those would it be?
No, I mean like because to me it looks just like a line, and then it goes like this, and then like that. And I don't.
I need to graph it. Is what you're telling me.
Either I can
Because
read
I
it.
can't see where you're.
Oh,
It's not right.
can I see that? It might be right. Let me flash it up.
That's what I got.
So do you guys get that for your graph? Okay, cool. Yeah, I'm feeling pretty good. So what's your question now? So you're talking about the negative infinity to 0?
Yeah.
So you're talking about this guy right here, right?
It's like a line to me.
No, it's not a line. No, no way.
If you zoomed in.
If it's curved like this.
Oh.
It's definitely curved. And that sound like Rain Man. Awesome. Let's say it went from negative 3 to 10. Sure. See what happens there. It's a little easier to see that maybe now. Maybe not?
Yeah, I just see what you're saying now.
Okay, but this right here is concave up, right? Even though the value is going down, this is concave up. Right here it switches, right? Switches. This is my inflection point, and now it's going concave down. This is concave down. Okay. If you thought, and I always do kind of an extension of these when I do concave up or down. If I were to take this guy and just kind of continue the pattern that I should have done, that would have been concave up right there, and then likewise, if I were to flip that over, that'd be concave down. Yeah.
So if it ended up being a line, would it not just, it wouldn't have?
It wouldn't have any concavity.
Okay,
Right.
so like if.
Because think about what, right? Think about if it were a line, right?
Yeah.
Give me a line. Make up a line.
2x.
2x. Take the derivative of that.
2.
2. Take the second derivative of that.
The-
0, right? So 0 is that positive or negative? Not really sure, right? So we can't tell concavity just
Okay.
based on that, right?
Okay.
So yeah.
Okay, so. But so how did you get a negative and a positive when it's going in negative direction the entire time?
Because I'm doing the second derivative. You're thinking of the first derivative, which is increasing or decreasing. Okay. If I were to talk about increasing or decreasing here, I would set the first derivative equal to 0, and then that would give my test intervals, which I'd still have this point right here. This would still be a point, but this right here would be decreasing. It would hit that point. It would actually be decreasing again, and we would get this value for our second derivative equals 0, wherever that bottom is right there. We would get that value, and then it switches back to increasing. So the first derivative tells you increasing or decreasing. The second derivative tells you concavity. Tells you what type of increasing or decreasing it is. It doesn't tell you if it is increasing or decreasing. That's what I was saying. Is it doesn't tell you if the graph is increasing like this, or if it's increasing. If it's concave up like this, or if it's concave up like this. Both of those are concave up, right? And we don't know which one's increasing or decreasing. So we have to do the first derivative to find out increasing or decreasing. Okay. So yeah, what's up?
I'm so confused. On the first graph that we graphed, the parabola, not parabola.
Oh, okay.
the-
Very beginning. Yeah. I'm with you.
Why is the inflection point's like not on a vertex, like, cause
Not on a
it looks
vertex?
like it would, you know how like, how there's the two vertex things, and it was like on 0.
I'm confused. Let me graph it again.
So my, yeah, like why, how come the inflection point isn't at one of the vertexes when it like switches?
Why is it switch in the middle?
Yeah.
That's what she says.
Why is it switch in the middle? Because
Yeah.
on this part from here to here, it's still the slope of a tangent line would still be on the top right here, and then once you hit this point right there, that's when it switches. It's like if I had a curve that went like this, right? This point right here, draw the tangent line to that point. It'd be kind of weird. It'd be like on one side here and then on the other side there, right? It'd be kind of a weird tangent line. So that's why it's kind of tough to draw those tangent lines because it goes through the line. Which we don't really like doing that. So, but any point on here, any point above it, then the tangent line is still on the outside, strictly on both sides. And then once I cross over that inflection point, any tangent line is now on the other side of it. Okay. So this magical point right here is where that tangent line bumps to the other side. It goes top of one side and the bottom of the other. Okay. Is that a little bit better? Or, so it's not gonna happen at a maximum minimum. However, it will happen at a maximum minimum on the graph of the derivative. So if you graph the derivative of this, which was that parabola, right, the max min there, that's where the inflection point happens on the original function. Okay? But you gotta like break it down a couple levels before you get there. So. All right, cool. Let's do a couple more here. Thank you. All right, cool. Never. Okay, let's do. You guys are feeling pretty good about this, right? Yeah. Do any of that? We don't have to do any of that, do we? Okay, let's do a second derivative test. Be good.
Oh, is it another one?
This is what you were talking to me about this morning?
No. I've already gone on my rant. It was a little rant. It was tiny. Second derivative test. Now remember the first derivative test, maybe.
Yeah.
Maybe. What was the first derivative test? You guys remember that one?
If you have, it's going to be a max.
Yeah, if it was increasing and then it switched over to decreasing, right? And then that FC value right there, well, the slope was 0, right? Well, that's how we set up our intervals anyways. That was a relative maximum. And then if it switched, if it did the same thing, if it was going negative right here, switched over to positive, we'd have a relative minimum. Okay? You guys were all feeling pretty good about that? That was the first derivative test, okay? The second derivative test is just as easy, which is going to be awesome. It says this. It says if you have this, if you have the derivative at some critical value equals 0. Now remember, this is a fancy way of saying critical number. Okay, so you take the first derivative, you set it equal to 0, you find your critical numbers, right? That tells you possible relative max and relative min spots, okay? Now the second derivative test says, well, we're not really sure exactly if it's positive or negative or how that's going to work, although you could use the first derivative test. The second derivative test says this. If I take the second derivative at the same exact c value, okay, the c value which made the first derivative equal to 0, and if that guy were positive, okay, now we want to just think about the repercussions of this. If we have f prime of c, we have the derivative of c equals 0, which means the slope is 0, okay? And I have the second derivative as positive. Second derivative tells me concavity, okay? Now if it's concave, if it's bigger than 0, is it concave up or down? Concave up, okay? So this right here tells me that this is concave up, okay? So if I have a zone of a graph that's concave up, right, that means it would look something like this. And if that c value right there, right at that c value, the slope is 0, right? So what does that tell you about the c value? That's a relative minimum. There you go. Relative minimum. That's what the second derivative test tells you. That if you're
Relative minimum of
at the point C. So if you find critical numbers, you're going to find all these critical numbers that we've done before, okay? If you take that critical number and you plug it into the second derivative, which assumedly is easily found, plug it into the second derivative. If that's positive, then you have a relative minimum. Okay, now we're assuming this is continuous and differentiable and all that, blah, 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 okay, that kind of stuff, okay? But short and sweet, if the first derivative is a critical number, and that critical number is positive in the second derivative, is a relative minimum. Okay, so that hopefully makes sense. The other part of that is just backwards. If I plug in that C value and it happens to be less than 0, that makes it concave down. Okay, so if I have a concave down zone, which means it's going to look like a cup facing down, and right at that C value, the slope was 0 on my original graph right there, right? Relative maximum.
So that's just another way to figure out relative maximum.
Another way to figure out relative maximum, relative minimum. Yep. Right.
Well, you saw it.
He's not going to plug stuff in, but that's the general idea. Okay? All right.
What if
Well. Oh, there's one last little thing. I like it.
Sure.
Let's say it equals 0. Ooh, weird. So that means I have a critical number, right, or a potential critical number where the derivative equals 0, right? Doesn't mean it has to be a critical number there. Like on the last graph we just did that I put up there, right? The first derivative would have given me 0, wouldn't have been a critical number. Okay. So my critical number actually equals 0. What does it mean when the concavity equals 0? Is it concave up or concave down? We don't really know, right? We can't tell. Concave up, concave down, we don't know, so test fails.
I thought it was an inflection point.
It's potentially an inflection point. Just because it equals 0 doesn't automatically make it an inflection point. It has to switch. If you set up your intervals on both sides of 0, let's say, right? I'm sorry, if you set your intervals on both sides of this guy, it might be concave up and concave up, might be concave down and concave down. It might be constant. It might be flat all the way through. Who knows? But if it equals 0 right there, the test fails. Okay? So we don't know if it's concave up or concave down. We're not really sure. Okay? So test fails if it equals 0. Okay? Unlike on the last one, the test did fail. So. All right, one real quick. Find some relative extrema using the second derivative test. Hopefully this will be quick and easy. Let's go ahead and do f of x equals a negative 3x to the 5th plus 5x to the 3rd. Now I want to find relative maximum, relative minimums using the second derivative test if I can. Now, I might do a whole bunch of stuff on this problem just to have it all said and done, okay? So I'm going to go ahead and graph this, and so we get a little visual here. Doesn't hurt as you're learning to throw these up here just to see what the heck it's going to look like. But as you get better at these, you'll restrain and refrain yourself. Looks like I could probably zoom in a little bit even, make it a little pretty. Maybe. Okay, so it looks something like that. And you might not have seen that if you hadn't zoomed in, right? Yeah. What was that chapter called? I looked up in that calc book. Do you remember what it was called? Hidden. Yeah, finding hidden secret. There was a section of my calc book. But anyways, if I were to just roughly look at this graph, right, and I should be able to just ballpark this just by looking at the graph, right? Looks like if I were looking at this, I would have increasing from negative infinity to looks like negative 1. Decreasing. Increasing from negative 1 to 0, increasing from 0 to 1, and then decreasing from 1 to infinity. Concavity-wise, it looks like I'm concave up from negative infinity all the way to somewhere in here. Don't know exactly where that point's going to be, but somewhere here looks like it switches, and it kind of goes over to a concave down. Concave down here, switches here, right? So right here it switches back to concave up. Concave up, concave up. Right in here somewhere it switches again, goes concave down, and it's going to be concave down forever. Obviously, relative max and relative min are pretty easy to see. Okay? So I potentially have 3 inflection points. I've got a point of inflection probably in here somewhere, right? I have a point of inflection here, and then a point of inflection somewhere in there. So those are the 3 values that I'm searching for on all this. Now, I want to find the relative max, relative min using that second derivative test if I can. So let's go ahead and find everything that we've done so far. First, let's go ahead and find the first derivative. And so that's going to be a negative 15x to the 4th. And then plus 15x squared. So I want to find possible critical numbers for this guy. Potential spots where this could be a maximum or minimum. So I'm going to set this guy equal to 0. Okay, so we factor out a negative 15x squared, and then you're left with x squared minus 1 equals 0. So 0 and then plus or minus 1 are my 3 possible critical numbers. So these guys are the critical numbers. Okay, which means at 0, 1, or negative 1 is potentially where a maximum or minimum could happen. Now, these are my possible critical numbers right here. But if you notice, just by looking on the graph, not all 3 are critical numbers, right? 0 is not a critical number. there. It's not a maximum or minimum, so I'd probably want to throw that out if I were saying these are my actual critical numbers. Okay. So those are my possible critical value or critical numbers. Now what I want to do is I just want to do the second derivative test real quick to see which one of those values would be a maximum or minimum. So if I can find the second derivative real fast, right? Just take the second derivative of this equation right here. That would give me negative 60x to the third plus 30x. Okay, so very short and sweet. If I want to find a relative max or a relative min, I'm just going to plug in my critical numbers, or what I think are critical numbers, into my second derivative. If it's concave up, that means it's a minimum. If it's concave down, that means it's a maximum. Okay. So if I plug in the value 0, right? If I plug in 0 there, what happens? Test fails, exactly. Yeah, that equals 0, so fail. You get that out. I used to love those commercials. Okay, now do the second derivative at -1. So plug in a -1 and see what value you get. All you care about is if it's positive or negative. You don't care about the actual value, okay? Plug in a -1. That gives me a negative, and a negative is positive, so a positive 60, and then minus 30, so this would be a positive value, right? Which means this guy is going to be concave up. If I have concave up is like this, that means I have a relative minimum. Okay, does that match on the graph? Looks pretty good. Relative min at -1. Feeling pretty good about it. Okay. Now let's go ahead and find that other relative max. Second derivative of the value 1. So plug in a value of a 1 there. Right? That's going to give me a negative value if I plug in a 1 there, which means it's concave down. If it's concave down, and the slope is 0, then this is going to be a relative maximum. So kind of a nice, easy way to find relative max, relative min. Find your critical numbers, plug those into the second derivative, and then find out which one works. This one's kind of the bugger right there is when the test fails. And that happens every once in a while. Okay? And obviously it failed on my graph too. It doesn't make sense there. Okay? All right, does that make sense? I hope to everybody. So far, so good. Yeah.
So we don't have to figure out like what makes the second derivative 0.
It depends if we want to. It depends what they're asking. It depends if they want to find concavity. Okay. Like if I said find increasing or decreasing, right? You would set up zones based on 0, 1, and -1, right? You would go negative infinity to -1, and then you would go -1 to 0, and then you would go 0 to 1, and then 1 to infinity. That would give you the parts where it's increasing or decreasing, right? Let's say I wanted to find concavity now, right? Or possible inflection points, just to make sure that I did it right, okay? If I were to do possible inflection points, I would set the second derivative equals 0, right? And factor that guy, so that would be, what, a negative 30x. And then I'm left with x squared, let's see, minus 2 equals 0. And so then my possible inflection points are at 0, and then plus or minus the square root of 2. So those are my possible inflection points. Okay, now, so that means I can set up intervals for concavity now, right? I can go from negative infinity to negative square root of 2. I can go from negative square root of 2 to 0. I can go from 0 to square root of 2. And then I can go from square root of 2 all the way to infinity. This will tell me concavity now, okay? So there's two basically different interval zones that you could be picking or choosing from, okay? These ones you plug into the first derivative, find increasing and decreasing. These ones you would plug in to the second derivative to screw up. I probably use
switch.
Yeah,
It should be 2x.
it should be minus 1
And 2x squared.
and 2 and then 1, right? Yeah. Okay. Yeah, I got my 1 and 2 back. Okay. So it should be 2x squared minus 1, which is going to be the square root of, now what, a 1/2 now?
Yeah.
So, which is kind of gross. That's, what, 0.707 or so. So if I were to check those points on my graph just to make sure which inflection points are actually going to work, if I go to second calculate value, I can just type that in. Now, I don't think if I go to second calculate, I don't see anything in here that says inflection. Okay, just so you know. Okay, so value, plug it in, 0. Okay, awesome. That's an inflection point, right? So you can tell that's good. What about, so these would all be different, right? I meant to put over 2s. I don't know what you guys are talking about. That's good. Okay. Okay, so let's say I typed in square root of 2 over 2, or let's go to the square root of 0.5, right? That gives me, that looks like about right. Looks like it could be switching from concave up to concave down right there. And then likewise a negative square root of 0.5 as well. And I get the same about spot. Okay, so I feel good. Yep, what's up?
Does multipliers cause negative radical 1 divided by 2?
Yep.
Is it negative radical 2 over 2?
This reduces, because the square root of 1/2 is the square root of 1 over square root of 2, which is 1 over square root of 2, which reduces to square root of 2 over 2.
Same thing.
So they're just equal. I just rationalized it.
It's a radical.
Yeah. I was saving my bacon. That's all I was trying to do. No good reason. Make them all .707s for all I care. It doesn't matter. All right, cool. We're feeling pretty good about this. Not too bad. Unfortunately, we just added a little bit more to your, repertoire of derivative stuff. It doesn't get much more as far as the graphing goes, though. So we've done most of everything. We got a couple more things to talk about, but
Do you
we're
have a
almost
third derivative?
there's no third derivative test. I know.